Welcome to the next video in an introduction to machine learning. Previously, we gave some resources. Now it's time to discuss the data. So questions you might have coming into here: what data set is being used and how do some of the variables look? We're going to tackle that by briefly describing the data set and then taking a peek at some variables. Let's start with our coding finally. So what I've done is I've got the notebook that we'll be using on Kaggle in a separate window so that you can see both side by side. And we recommend you do this as well. So you have the lesson and the notebook here. We can now finally start with some coding. During the lesson, there are these code blocks indicated by this Python banner. And what you can do is copy and paste them into the notebook. And then to run the notebook, you can do Shift and enter in that cell, and then that runs. So this is importing Pandas, NumPy, and Matplotlib, which are three libraries we'll be using. Going to seed the random numbers to have some more reproducibility. And now we can talk about the data set being used. So we're going to use Atlas data. Our signal is Higgs boson decay, and background is non-Higgs boson decay. Various physical quantities such as lepton charge and momentum are recorded for each event. This analysis loosely follows the discovery of the Higgs boson. So here we're only going to process the main background and main signal. So first of all, the main signal, GGH125 ZZ4LEP, and the main background, LLLL. Now we can start exploring the dataset. So let's read our dataset into Pandas data frames from the CSV files that are saved in this notebook view. For each sample, the CSV file is read in from the input folder here, and then at the end is printed. So you can have some idea of what the data look like here. These are the column names, each column here, and the rows are for each entry. For the signal first, and there are a number of columns, so it keeps going there. Lots of columns. And it finishes there. And then same thing for the background. Before diving into machine learning, you should always think about whether there are any things you should do to clean up your data. In the case of this Higgs analysis, Higgs boson decays should produce 4 electrons, 4 muons, or 2 electrons and 2 muons. So let's define a function to keep only events which produce 4 electrons, 4 muons, or 2 electrons and 2 muons. I'm going to call it cut_lep_type. Run that notebook cell. Then we need to apply this function to our data frames. So what that's done is it's kept only the entries for which that's true when there are either 4 electrons, 4 muons, or 2 electrons and 2 muons, and it's thrown away the entries where that is not true. So that's done something to clean up our data. And then the data are printed again. The data that remain, that is. Now we've got a challenge for you. Another cut to clean our data is to keep only events where lep charge 0, lep charge 1, lep charge 2 plus lep charge 3 equals 0. Write out this function yourself, then apply it. So the idea here is to pause the video, use this example to try and work it out yourself, think about it, ask if you've got a particular question, and If you're still not sure, you can click right here to look at the solution. So pause this video and try work it out yourself. You can resume it once you've given it a go. Okay, now let's talk through our cut lep charge. So first we define a function where the input, rather than being the lepton types, is the lepton charge. We calculate the sum of the lepton charges, similar to the sum of lepton types. And then if the sum is 0, we want to keep that event, return true, or else return false and throw it away. Then we apply that cut. So we loop over the samples as here. We do this vectorize called cut lep charge on the data frames with lep charge 0, lep charge 1, and 3. And then the same thing as before, the new data frame with only events passing those cuts is printed. So signal first. These are the rows that have passed those cuts. And then background. Okay, now it's time to plot some input variables, because in any analysis searching for signal, one wants to optimize the use of various input variables. Often this will be to find the best signal to background ratio. So here we define some histograms that will look to optimize. First of all, LEP-PT2. Copy and paste this in. We've got the bin width of the histogram, the number of bins, where we start from on the x-axis, and an x label. Now, a small challenge for you, write a similar dictionary of plotting parameters for LEP-PT1, the only difference being that we're wanting to use 28 bins rather than 13. So pause this video and try and work it out yourself, and then you can click here. It's the exact same thing, but we changed 2 to 1 and changed number of bins to 28. Okay, now we define a dictionary of LEP-PT2 and LEP-PT1. Now we can take a look at those variables. Because the code is a bit long, we've predefined this function for you to illustrate the optimum cut value on individual variables. So let's call this function. It's important to note we're not doing any machine learning just yet. We're simply looking at the variables that we'll later use for machine learning. If you are interested in seeing how this function works, you can see the link here. So let's talk through the LEP-PT2 plots. I'm just going to zoom out here to be able to have them both on the same screen. On one screen, that is. Okay, so first step. Imagine placing a cut at 7 GeV in the distributions of signal and background, this upper plot. This means keeping all events above 7 GeV in the signal and background histograms. We then take the ratio of the number of signal events that pass this cut to the number of background events that pass this cut. This gives us a starting value for S over B here in the second plot. Now, third step, imagine increasing this cut value to 8 GeV, 9 GeV, 10 GeV, 11 GeV, 12 GeV. What that means is all events above that value are kept, and all of the events below that value are thrown away. And then, again, take a ratio of the total number of signal events passing those cuts to the total number of background, getting a new value for S over B. So increasing these values is throwing away more background than signal, so S over B is increasing. But there comes a point 4, around 13 GeV, where we start to throw away too much signal. Therefore, S over B starts to decrease. Our goal is to find the maximum in S over B and place the cut there. The same logic applies to the LEP-PT1 plots. So pause this video and see if you can talk through that logic to yourself. Now then, once you've done that, it's important to note that in the Atlas Higgs discovery paper, there are a number of numerical cuts applied, not just LEP-PT1 and LEP-PT2. Imagine having to separately optimize 5, 6, 20 variables, not to mention that applying a cut on one variable would change the distribution of another, which would mean you'd have to re-optimize. Sounds like a nightmare. This is where a machine learning model, such as a neural network, can come to the rescue. A machine learning model can optimize all variables at the same time. It not only optimizes cuts, but can find correlations in many dimensions that will give better signal to background classification than individual cuts ever could. So that's it for why we want to use a machine learning model. Stay tuned for how to actually use one. Key points from this lesson is that you must know a bit about your data before any machine learning, and it's a good idea to visualize your data. See you in the next lesson on data pre-processing.